This video is about exact differential equations. We're going to review what an exact differential is from Calculus 3, and then we'll talk about what makes a differential equation exact. And then I will tell you how to find the solution of an exact differential equation. And then we'll work this particular example, work our first example. So the easiest way for me to think about this is in terms of exact differentials from Calculus 3. Now in Calculus 3, you learn about functions of two variables, and we often represent these as surfaces. So if we let z equal f of xy, for every xy in the domain of this function, so we're in three-dimensional space, for every xy in some domain, we map to a particular value of z. And as we go through all of the different points in the domain, we end up with some surface. Might end up like something up here, just in general. So that's our surface. Now let me give you a specific example. Let's say that z is equal to x squared plus y squared. Well then if x and y are both 0, z is 0 squared plus 0 squared, so z is 0. And when z equals 1, we have a circle of radius 1. So we're going to see a cross section that looks like this. And when z equals 4, well then we would see a circle of radius 2. So we'll go up 4 units. That's 1, 2, 3, 4. And then I would see a circle of radius 2. And when you put all of those together for different values of z, as z increases, the radius of that circle increases, and we end up with something that looks like this. This is called an elliptic paraboloid. And we study these more in Calculus 3. We call it an elliptic paraboloid because slices this way are ellipses parallel to the xy plane. They're actually circles for this particular example. And if we slice it other ways, if we let x equal a constant, then we get parabolas. The cross sections are parabolas. Or if we let y equal a constant, the cross sections are parabolas. So together, we call it what we call an elliptic paraboloid. Now, if I take my elliptic paraboloid and I focus on what's called a level curve of this surface. So I'm going to focus on this one. So that's where z is equal to 4. So I'm at a constant height of 4 above the xy plane. Then my equation looks like this, and I've got x squared plus y squared equals 4 on this side. Now, if I want to take the derivative of both sides, or alternatively take the differential of both sides, then this makes sense in the following way. We say that the differential of f in Calculus 3 is defined to be the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Now, if you haven't taken Calculus 3 yet, that's okay. It's not a prerequisite for this class. But the way you take partial derivatives is pretty much what you would expect. I'm letting x vary and I'm treating y as a constant. So it's as if I'm on a plane where y is equal to, say, 2. And I said, if y is equal to 2, what's the derivative of this with respect to x? And we would just get 2x. And then when I'm taking the partial with respect to y, I'm treating x as a constant and differentiating with respect to y. So maybe x is equal to -1. If x is a constant, the derivative of that constant with respect to y is 0, and the derivative of y squared is 2y. So the differential of this expression, x squared plus y squared, according to this, is the derivative of this with respect to x, which is 2x, times dx, plus the derivative of this part with respect, or derivative of the whole thing with respect to y, which is 2y, times dy. And that's equal to the differential of 4. In general, it's just going to be 0. So we end up with this equation. It's a very simple equation. 2x dx plus 2y dy equals 0. That's a differential equation. And basically our goal is, instead of going from here to here by taking differentials, we want to go from here back to here. We want to find that function f of xy that generated this right-hand side. This is called the exact differential of this function f. Or sometimes people will just call it the total differential of f, or just the differential of f. But if I start with an equation like this, the solution is a curve that looks like this. It's going to be f of xy equals a constant, because the derivative of that constant would give me 0. Okay, so an exact differential equation is an equation of the following form. We say that m of xy times dx plus n of xy times dy equals 0 is an exact differential equation, or an exact DE, if this left-hand side is the differential of some function f. I'll say if df equals m dx plus n dy for some function f. So if this left-hand side is the exact differential of a function, this is an exact differential equation, then the solution curve is a level curve of some surface. So it's where that, if I take that surface and I just slice it with a plane that's parallel to the xy plane, so z is equal to a constant, it's going to be a level curve of that surface. The solution curve is the graph of this relationship when I undo this sort of differentiation process. I'm going to have f of xy on this side. And on the other side, I'm going to have k, because the differential of this is this, and the differential of a constant is 0. So this is actually a level curve, or just a curve where that z value is constant on a function of 2 variables. Now, if you haven't had Calculus 3 yet, don't worry. You don't need to understand all of this completely in order to solve exact differential equations. I would love it if you understood it completely, because I never want you to just follow a process to find an answer. I want you to understand the process and understand exactly what it is we're doing. But the idea is this, that if I have a differential equation like this, and this is the exact differential of some function, then this is the solution, or an implicit solution of that differential equation. Okay. So the question becomes, how do you find it? Or how can you even tell if a function or if a differential equation is an exact differential equation? Well, it's actually not too bad. We know that this is an exact differential equation if the following is true. If the partial of m with respect to y is equal to the partial of n with respect to x, then the differential equation is exact. And you might be saying, why is that true exactly? And let me remind you, if this is the exact differential of some function f, then this is the partial of f with respect to x times dx. And this is the partial of f with respect to y times dy. So the only way, the only way that this is an exact differential is if these are equal to each other. And the only way these are equal to each other is if m is equal to the partial of f with respect to x and n is equal to the partial of f with respect to y. If those are equal, then we're dealing with an exact differential. And say, well, how can you be sure that this function, that there's a function out there where m is the partial of f with respect to x and n is the partial of f with respect to y. Maybe there's not even a function out there that exists like that. In that case, it wouldn't be an exact differential. Well, one way you can check is you can take the mixed partials of f. So I've got the partial of f with respect to x here. If I take its derivative with respect to y, that's the partial of f with respect to x and then y. If I take the derivative of this one with respect to x, that's the partial derivative of f with respect to y and then x. So we're getting mixed partials for second partial derivatives. If those are the same, if the mixed partials are the same for that function f, or if the partial of this one with respect to y is the partial of this one with respect to x, well then we're saying that there's a function out there, f, where this is satisfied. The partial of f with respect to x is this, and the partial of f with respect to y is that. Okay. Ask me questions if you need to about the details with that. Okay, so in practice, if you have a differential equation and you want to determine whether or not it's exact, you're just going to check this condition. You'll identify m and n, and you take those partials. If they're equal to each other, the differential equation is exact. Now, this is a really simple one. If this is my m, and this is my n, the partial of m with respect to y is 0, and the partial of n with respect to x is 0. And so that's nice. The partial of this one with respect to y is equal to the partial of this one with respect to x. And if you're not sure, you're like, what variable am I supposed to take the partial with respect to? It's the opposite of the variable that's multiplying it. So when I see a dx times this m, I know I want to take the partial of this one with respect to not x, but y. When I see this one times dy, that means I need to take the partial of this function with respect to not y, but x. So I'm taking the partial of this one with respect to y, the partial of this one with respect to x. They're both 0, so that means it's exact. In order to find the original function, we'll have to do some antiderivatives. But that's a really simple one. Most of the time, when we're working with an exact differential equation, it looks more like this. So we're going to solve this one instead. This is from section 2.4 of the ZIL textbook. It's a first course in differential equations with modeling applications, 9th edition by ZIL. You can see it down here, Dennis G. ZIL. So yeah, that's where I got this one from. So most of the time, we're not working with a function as simple as x squared plus y squared. We're working with a much more complicated function. But let's work this one now. If I want to determine if it's exact, I need to identify m and n, and then check those two partial derivatives. So I've got e to the 2y minus y times cosine of xy. And then I've got all this over here. This one's got a lot going on, doesn't it? The function multiplying dx, we're going to call that m of xy. The function multiplying dy, we're going to call that n of xy. If the partial of this function with respect to y is equal to the partial of this function with respect to x, then the dE is exact. So we'll say verify that the dE is exact by checking those partials. So we want the partial of m with respect to y. So that's Leibniz notation. Alternatively, you can use subscript notation. Or you can use operator notation. This is the partial with respect to y of this function. Now, be very careful here. We are treating x as a constant, and we're differentiating with respect to y. That's how we take partial derivatives. So the derivative of e to the 2y is e to the 2y, so derivative of an exponential is an exponential, times the derivative of the inside with respect to y, treating x as a constant. The derivative of 2y is just 2. Now over here, I've got a function of y times a function of y. So I'm going to have to use the product rule. So according to the product rule, we're going to get the derivative of the first. So I'll say plus the derivative of the first with respect to y. And multiply by the second function. And then we'll add the derivative of the second function with respect to y. And we'll multiply by the first function, which is negative y. Okay, and then the derivative of negative y with respect to y is just negative 1. And then the derivative of this piece, derivative of cosine of something, well, derivative of cosine of a function is negative sine of that function, times the derivative of the inside with respect to y, treating x as a constant. So I'm taking the derivative of xy with respect to y, and I'm thinking of x as a constant. So I want to look at this and think of it as a constant times y. The derivative of a constant times y is the constant, and the constant in this case is x. So that's what I get there. Let's keep going. So we have 2e to the 2y minus cosine of xy. And then I've got a negative times a negative, that's a positive. And an xy, I'll put that out front. So I've got xy times sine of xy right there. So that's a partial of m with respect to y. Now we want to take the partial of n with respect to x, and our hope is that we get exactly the same thing. The partial of n with respect to x, or in subscript notation, n sub x. The partial with respect to x of this function, 2x times e to the 2y minus x times cosine of xy plus 2y. Okay, now x is your variable, and we're treating y as a constant. So this is all a constant times x. That's how I have to think about it when I take a partial derivative. The derivative of a constant times x is just my constant, which is e to the 2y. Then over here, I've got a function of x times a function of x, so I have to use the product rule again. So I want to add the derivative of the first with respect to x, treating y as a constant, times the second, undifferentiated, and then we'll add the derivative of the second function with respect to x, treating y as a constant, times the first, which is a negative x, undifferentiated. And then we're adding the derivative of 2y with respect to x. That's just a constant. The derivative of a constant with respect to x is 0. Okay, so now I need to work the rest of this out. The derivative of negative x with respect to x is negative 1. And the derivative of cosine of xy is negative sine of my angle times the derivative of the inside with respect to x, treating y as a constant. Well, if y is a constant, this is a constant times x. The derivative of a constant times x is just the constant. And so I get 2e to the 2y minus cosine of xy. A negative times a negative is a positive. X times y comes out front, and this is sine of xy right here. And the question is, are these two guys equal to each other? We've got 2e to the 2y, 2e to the 2y, minus cosine of xy, minus cosine of xy. Hey, they're exactly the same. That's great. So these two partial derivatives are the same, and that means that the differential equation is exact. Okay, now that we know the differential equation is exact, well, that tells us that there is a function out there. So we say there exists a function f such that the following is true. The differential of f is m dx plus n dy. Now, sometimes, rather than writing it in this form, mathematicians like to use shorthand. So I'm going to show you some shorthand now. There exists is just this backwards e. So we're going to say there exists an f, or f of xy, such that the differential of f is m dx plus m dy. Now, by definition, the differential of f is the partial of f with respect to x times dx plus the partial of f with respect to y times dy. Or if you prefer, you can use Leibniz notation. I'm writing it both ways just as a reminder. This is exactly the same as this. This line and this line are the same. This is just an alternate notation. I like subscript notation a lot, but since we use subscript notation differently in physics class, well, sometimes I want to use this. Or sometimes you just have to remember from context that since you're in math class, subscripts indicate partial derivatives. Okay, so there's some function f out there that satisfies this, and we want to find it. Because the solution to this differential equation is a level curve of that function. It's f of xy equals some constant k. We want to find f. Now, the only way this is equal to this is if m is the partial of f with respect to x, if all of these are equal. And if n is the partial of f with respect to y, so all of those are equal. So if this is true, that means this is true. And m was this function, I'm reading it off of the other page, e to the 2y minus y times cosine of xy. And at the same time, the partial of f with respect to y is n, and that is 2x e to the 2y minus x cosine of xy plus 2y. Now there are a couple of different ways that you can solve this. And either one of, there are several ways that you can solve this. Any of those ways is fine. I'm just going to show you one of those ways, one version of the method. If I have the partial of f with respect to x, and I'm trying to get f back, I just take the antiderivative. But it's just a partial antiderivative, right? It's not going to give me f back, it's going to give me f back partially. So if I'm trying to get f back from the partial of f with respect to x, I have to take the antiderivative of the partial of f with respect to x with respect to x. So that is, in this case, the partial of f with respect to x is m, and m was this. So we just need to evaluate this integral now. Now remember, y is being treated like a constant and x is your variable. So this is just a constant. The antiderivative of a constant with respect to x is that constant times x. And here, negative y is just a constant, so I'm going to bring it down. And then I'm going to ask myself to find the antiderivative of cosine of x times y with respect to x. The antiderivative of cosine is sine, but I've got a constant times x inside. That's a y, which is a constant, times x. If that was a 3x, the antiderivative of cosine of 3x with respect to x would be sine of 3x, and then we divide by that constant 3. And we're doing that because of that kx modification of our rules, or you can think of it as a very simple use of. If I were taking the derivative of sine of 3x, I'd have to multiply by 3. Take the antiderivative, I have to divide by 3. So this time, instead of having a 3 in there, I've got a constant y. I'm thinking of y as a constant. So the antiderivative of cosine of xy is sine of x times y, where y is a constant. And if I were taking the derivative, I'd have to multiply by y. Since I'm taking the antiderivative, I have to divide by y. Now be very careful here. F of xy is equal to this function plus not a constant of integration, but something that is constant with respect to x, but not necessarily with respect to y. So I'm going to call that g of y. the partial derivative of g of y with respect to x is going to be 0 because there are not going to be any constant, or there's no x's in it, so it's constant with respect to x. And of course, these y's reduce. So f of xy is x times e to the 2y minus sine of xy plus g of y. So it recovered f almost up to this function g of y. I just need to figure out what that function g of y is, and then I'll be done. Then I'll know what f is. So we're going to take a different approach. This recovers f partially by taking the antiderivative of the partial of f with respect to x with respect to x. And I also have the partial of f with respect to y. So you can probably see where I'm going with this. In order to get f back from that, we have to take a partial antiderivative with respect to y, because we're undoing that operation of partial differentiation. So we've got the antiderivative of 2x times e to the 2y minus x times cosine of xy plus 2y, and that's all with respect to y. So first thing I'll do is I'll bring down this constant. X is being treated as a constant this time because we're anti-differentiating with respect to y. To bring your constant down. The antiderivative of e to the k times y is e to that power, and then we have to divide by the k. Just as a reminder, the antiderivative of e to the kx is 1 over k times e to the kx plus c. And remember that 1 over k is compensating for that multiplication by k that comes from the chain rule. If I'm taking the derivative of this, I have to multiply by the derivative of the inside. The derivative of the inside is a constant. When I'm undoing that, I have to divide by that constant. So we're doing the same thing with the 2 here. If I've got an e to the 2y, the antiderivative is e to the 2y divided by the 2. X is a constant here, so you bring that down. And then you ask yourself, what's the antiderivative of cosine of xy? Well, it's sine of exactly the same angle, but I'm treating x as a constant. So this is a constant times y. The antiderivative of cosine of a constant times y is sine of that constant times y divided by that constant. For the same reason that we divided by that 2, we're dividing by this x because we're treating it as a constant with respect to y. And the antiderivative of 2y with respect to y, this comes from bringing the 2 down, adding 1 to the exponent, and dividing by the new exponent by the power rule, and those 2's reduce. So you did this part, and this part, and now you have to add a function that is constant with respect to y, but not necessarily with respect to x. So let's call it h of x. And we've got x times e to the 2y here, minus sine of xy, plus y squared, plus h of x. Now both of these are f of xy, and we're trying to find f of xy in general. So this has to be equal to this. Well, according to this, it has an x e to the 2y in it. This also shows me the same thing. According to this, it has a negative sine of xy. And then it also has some arbitrary function of y. So that's right here. Question is, what is that function of y? In order to figure out what that function of y is, I have to compare it to what doesn't match over here. These two pieces match, so we know that f of xy has that in it. So we write that down. And then I have to match these two terms. So g of y has to be y squared plus h of x. Well, it looks like if this is g of y and this is y squared plus h of x and there's no x's over here, h of x must be a constant. So then I'll have y squared plus a constant equals y squared plus a constant. That's going to work. So we're going to have a y squared plus a constant here. I'll just call it c. Okay. Now, the solution of the differential equation is not f. Remember where we started. The solution of the differential equation is f of xy equals a constant k. In this case, k was 4. In general, it's just going to be f of xy equals a constant k, and we can find the value of k if we have an initial condition. But we didn't have an initial condition this time. So the solution of the differential equation is f of xy which turns out to be this function. And then you have the plus c equals k, and then that's k can absorb the c, so you just have the k there. And this is an implicit family of solutions, but we're not even really thinking of it as an implicit family of solutions. We're more thinking of it as a level curve of a function that looks like this. So we're saying when z is equal to k, and k might be 100, I'm slicing this surface. And we're saying that that slice is a solution of this differential equation. So if I take the differential of that slice, I get this, and that's the differential equation. Okay, so brief recap. What makes an exact differential equation exact? Well, if this is the exact differential of some function, then the solution to this is that function of f of xy equals k. And the question is, well, then how do you know if that's an exact differential of some function? You just check these two partials. Check the partial of m with respect to y and the partial of n with respect to x. If those are equal to each other, the DE is exact. And that means that there's some function out there for which m is a partial of f with respect to x and n is a partial of the same function with respect to y. We just need to find the function. If this is true, then this is true. So if I'm solving an exact differential equation, or if I'd like to solve an equation and I want to see if it's exact, I start by computing some partial derivatives. I identify m and n and compute the partial of this one with respect to y and the partial of that one with respect to x, which is what we did. Then compare them. If they're the same, the differential equation is exact. Then you've got this existence statement. If the differential equation is exact, then there must be a function out there, f, that satisfies this. And if there's a function out there, f, that satisfies this, then there's a function f that satisfies these two equations. You've got the derivative of f with respect to x and the partial derivative of f with respect to y. If you want to get f back, anti-differentiate the partial derivative with respect to x with respect to x. And you want to anti-differentiate the partial derivative of f with respect to y with respect to y. You're going to get two versions of the same function. To figure out what the function is in general, in the most general terms, you've got to match the parts. Anything that appears on both sides, that's definitely part of your function f. And anything that doesn't match has to match somehow. So this g of y must be that y squared, and since there's no function of x over here, that h of x must be a c. So this must be y squared plus c, and that would make this y squared plus c. So this satisfies this, y squared plus c, where h of x is c, and this red piece satisfies this because it's a function of y only, it's y squared plus c. And the solution of the differential equation is f of xy equals k, a level curve of this surface. And if we wanted to, we could graph that surface using something like CalcPlot 3D or another grapher. But yeah, it's just a slice of that surface where z is equal to the constant k.